So last time we talked about matter. We talked about different classifications of matter, right? Compounds, elements, mixtures, heterogeneous, homogeneous. We talked about changes and states. Today, we get into the other side of this chapter, which is energy. I assume everybody here has heard the word energy before at some time, right? You kind of have a sense of what that means. Anybody think you can really define it? What would be your, you said, I don't know what energy is. What is energy? How would you define it?
Capacity to work.
Capacity to do work? Yep. Any other ways you would define it? What?
Like what gets us going.
What gets us going? How we do stuff? So it's sort of the same thing, right? Capacity to do work, do things. And yeah, in fact, those are both great. And the technical definition is energy is the capacity to do work. So what does that mean? What's work? From this kind of a standpoint. What do we mean by do work? Or do things? What kind of work? Movement? Okay. What other kind of work can there be?
Force.
Force, yep. Force over a distance. Yeah, we're not going to really get into the physics of energy and work in this class, so go take some physics and you can talk about that. But right, so energy, there's a idea of the law of conservation of energy. Energy can't be created or destroyed, right? It can be transferred. So when I pick something up and put it on the table, I'm transferring energy from me to the bag. Now this bag has more energy, has more potential. And the way I know that is, if I dump it back off the table, I have to use energy to do that, right? The energy then gets released by the bag. So there's this idea that you can transfer energy around, it's capacity to do work. But there's another way that you can transfer energy besides work. Anybody know what it might be? What? Temperature, yeah, or heat, right? So if energy is the capacity to do work, heat is a type of transfer of energy. So work is also a transfer of energy. Work is a transfer of energy like we just talked about with the bag, whereas heat is a transfer of energy in a different way. So we'll talk about heat. We have to talk first about temperature. What is temperature?
Measurement of heat.
It's a measurement of heat? Okay. Anybody else want to talk about temperature? From a chemistry standpoint, we talk about temperature as the average kinetic energy of the molecules. So the molecules are moving around, and the temperature is the average energy of the motion of those molecules. How do we measure temperature? Yeah, let's talk about those different scales. So we've got degrees Fahrenheit, degrees Celsius, Kelvin, which notice is not a degree. I'll talk about that in a second. So these are the three main ways to measure temperature. And we're going to learn to convert among them. But the conversion is a little bit different from what we've done because these aren't factor conversions. They're a little bit tricky. The reason for that is that they not only have different size units, but they also start at different places. There's a nice picture in your book that compares this. So I'm going to copy this over. 65. So here are some thermometers in boiling water. You've got a Kelvin thermometer on the left, then a Celsius thermometer, then a Fahrenheit. So I guess it's completely opposite from what I wrote down. Let's change this just to make it look nice with the picture. So we've got Kelvin, we've got degrees Celsius, we've got degrees Fahrenheit. So let's look at where the temperature is right here. I think you can see it. There's a red line that stops right here. On the Celsius scale, which is the one we'll be using most often in this class, that's going to be 100 degrees C. That's boiling water. On the Fahrenheit scale, that's 212. And on the Kelvin scale, that is 373. And then let's look down at the freezing point of water, which is 100 Celsius degrees less at 0. So between 100 and 0, you've got 100 Celsius degrees, and you also have 100 kelvins. So Celsius and Kelvin, the degrees or the units are the same size. There's 100 of them between the freezing point and the boiling point of water. The Fahrenheit scale, it gets a little different, right? The freezing point of water on the Fahrenheit scale is 32. The boiling point is 212. So there's 180 Fahrenheit degrees in between those. So what does that mean? What does that tell you about the size of a Fahrenheit degree compared to the size of a Celsius degree? It's less. Fahrenheit degrees are smaller. All right? So that means when we convert among these scales, we not only have to convert the unit size like we would with centimeters to inches or something like that, or grams to pounds, we have to also convert the starting point. In our other units, 0 is 0, and everything starts at 0, whether it's pounds or grams or whatever. But on the temperature scale, we have to adjust for the starting spot. And so we have a multiplication or a factor term, and we also have an additive term to adjust the freezing point. I think the easiest way to deal with this is to just kind of remember these equations and think about what they mean. So let's write down these equations and then talk about what they mean. The easiest one is to go between Kelvin and Celsius. So the temperature in Kelvin is equal to the temperature in Celsius plus 273. Right? The degrees are the same between Celsius and Kelvin, the degree sizes. They're just offset by 273. Anybody know why that is? Why we have that difference? What that means? Do you guess?
Between Celsius
And Kelvin. Yeah.
So, because usually Kelvin is measuring even if it wanted to go under 0.
Right. Kelvin, the Kelvin scale starts at 0. There is no temperature colder than 0 Kelvin. That's called absolute zero, where the average kinetic energy of molecules or whatever particle is actually 0. So something can't be moving less than not moving, right? So 0 Kelvin is 0. There is no below 0 Kelvin. And so what that means is that we have to adjust for that offset. You have to get to 273 degrees Kelvin to get to 0 degrees C, because there's plenty of temperature room below 0 degrees C. Yeah, I mean, we get there in the winter every year. So that's where that offset comes from. So they're the same size unit, but Kelvin can't go to 0, so we have to have those extras 273. Can't go below 0, so we have to have those extra 273 degrees. So then how do you get from Kelvin to Celsius? If you get from Celsius to Kelvin by adding 273, yeah, you subtract. So if you're given a Kelvin temperature, you subtract 273 to get to the Celsius temperature. So temperature in Celsius is temperature in Kelvin minus 273. All right. So now let's look at the Fahrenheit and Celsius. So the temperature in Fahrenheit is 1 times the temperature in Celsius plus 32. I'm going to put both these equations down and then we're going to talk about them. The temperature in Celsius is the temperature in Fahrenheit divided by 1.8. I think. No, wait. Temperature Fahrenheit minus 32 first divided by 1.8. Yep. Yep, that's the other way to do it, is 9 over 5. So whichever way you like it is okay. So let's look at the reason for this. First of all, for the temperature in Fahrenheit. If you have a temperature in Celsius and you want to convert it to Fahrenheit, one thing you have to do is add 32. Because instead of starting at 0, where with, well, Celsius water freezes at 0, Fahrenheit 32. So that means there's an offset of 32. So that's where this plus 32 comes from. We also have to correct for the fact that a Celsius degree is larger than a Fahrenheit degree. Right? So we have to use this factor there. And the opposite is true for Celsius. So with the Fahrenheit, we have to subtract 32 to get 0, and then change the unit size. These are tricky equations to remember. It's not that they're fancy numbers or they're long or something, but the order of operations is really important. So when you convert from Celsius to Fahrenheit, in the first case, you have to do the multiplication first, and then you add 32. In the second case, going from Fahrenheit to Celsius, you have to subtract the 32 first, and then divide by 1.8. All right? What I recommend is to do this is to remember a couple of conversions. So remember that 100 Celsius is 212 Fahrenheit. Remember that 37 degrees Celsius, which is body temperature, is 98.6 degrees Fahrenheit. Remember a couple of those. And then if you're sitting there and you know there's 1.8 and there's 32 and you can't really do it, just do it with one of those numbers you know. And if you get the other one, then you know you've got it right. If you don't, then you don't have it right. Switch it around, try again. Does that make sense? Right. So if you keep a couple of those pairs in mind, if you get mixed up in the equation or it's an exam and you're stressed out and you can't seem to remember it right, you can try it, see what works, and you'll have your equations. Okay. There are lots of practice problems in this chapter converting these temperature things. And it's easy to do them with your equations sitting there. But what I would recommend is do the first couple with your equations there. Make sure you're getting it right, you're doing it right. And then slowly put the equations away. Don't look at them anymore. And just the practice, the repetition will get that into your head. Okay. All right. Now we know how to measure temperature. So now let's talk about heat in terms of a chemical process. I'll show you a couple words. Exothermic versus endothermic. Have you heard these words before? What do they mean?
Internal or external heat.
Has something to do with heat transfer. What do those prefixes mean generally? You heard exo versus endo? Yeah, exo means outside and endo means inside. So an exothermic process is one that releases energy to the surroundings. So energy goes out. This is going to be a process that releases energy. Somebody give me an example of an exothermic process. Anything in... What? Sweating. Let's see. I got to think about that and make sure that's actually right. So that's... Actually, sweating is the opposite because it cools you, right? So you sweat, it takes energy out. You. Yeah. So that's a tricky one. We'll come back to that one. Yeah, the sun and explosion. explode, anything that gives off heat, that gets hot, that's going to be an exothermic process. So burning, those sorts of things. We'll get to phase changes in a second because that's actually a really good point. And so an endothermic is going to be something that absorbs energy. So energy goes in. What's an endothermic process then? These are sometimes harder to find.
Plant taking in the sun.
A plant taking in the sun? Sure, yeah. So photosynthesis is an endothermic process because it requires energy being put in. Yeah. Other examples, well, like a really clear example, have you ever seen those portable cold packs? You like break a thing and it gets really cold for when you need to put it on an injury, something like that. That's a chemical reaction in there that's endothermic, so it's sucking all the energy in from the surroundings, which makes it really cold. So we're going to talk about these in the context of phase changes. And if I can find my thing here. But to do that, we also need to know something about units. Units of energy, which is also heat in this case, because heat is a transfer of energy. Anybody know a unit of energy? There's a few of them. Joules. What else?
Electrical, you know, like, would that be considered, so you say hertz or?
Well, this is a frequency. That's a measure per second. There are electrical potential is measured in volts. So that's a unit of energy that's specific to electrical potential.
What do you say in your gas bill all the time?
A therm, yes, that is, I don't know what that is.
Right.
Is that a unit of energy?
Yeah, you see it on the gas bill, they measure things. Right, right.
I know that we often see kilowatt hours.
Yes.
That's a measure of energy. Is my phone? Somebody's phone's making noise. So let me look that up, actually. I don't know.
So I could put volts as well.
Yeah, volts is a measure of electrical energy. Electrical potential. A therm is a unit of heat energy. That is also another unit of energy. Another one is a BTU, a British thermal unit, and a therm is 100,000 BTUs. I didn't know that. There's one more. We're not going to deal too much with therm BTUs in this class, but there's one more that we will. Calories. Okay. So in this class, we're going to focus on calories. Joule SI unit, or the metric unit, the standard unit, and calorie is a common unit that is used. 1 calorie is 4.18 joules. You don't have to remember that number, just going to show you that. And confusingly, this calorie is not the unit that's on our food. Anybody know why? What's the difference? Well, it's just off by a factor. So the calories on our food are C, calorie capital C, and with capital actually 1 kilocalorie, which is 1,000 calories, right? Kilo is 1,000. It's confusing the word, but the letter C is one of those letters where the uppercase and the lowercase kind of look the same. So if you don't draw it right, you could be off by. But this is the unit that's on our food, simply because a calorie is very small, and if we reported stuff in calories, those numbers would be really big, so it's easier to use a kilocalorie. In other countries, you'll often see kcal instead of the big C calorie. All right, so we're going to look at energy in terms of calorie. Anybody know where that calorie unit comes from? I'll tell you. It takes one little C calorie to raise 1 gram of water 1 degree C. 111. If you have exactly 1 gram of water and you want to raise a degree, so like 37 to 38 degrees, that takes exactly 1 calorie of energy. And that's how you can calculate a calorie. That's called the specific heat of water. And you'll be able to practice that a little bit using that in your book a little bit. Okay, we have a whole lot of time left. So with our remaining time, let's talk a little bit about phase changes. And to do that, I'm going to bring in a picture. Oh, I just deleted the picture, I think. Okay, I'll pull it out of the book. So this is page 81. I'm going to start a new page here. This is something called a heating curve. For water. So this is water. And what this shows is the temperature change over here on the upper axis, the temperature as we add heat. So you think for a normal substance, like whatever substance, as you add heat, the temperature increases, right? And that's usually true, except for a couple important spots. So we start off here at the bottom. We've got some ice at minus 40 degrees C. As we add heat, the ice warms. It gets warmer and warmer and warmer and warmer and warmer. And then all of a sudden, we have to add a bunch of heat. The temperature doesn't change. What does change? The phase or the state, right. It was solid, it becomes liquid. So what this shows is that it takes extra energy to change that phase. The reason for that is shown in these pictures. So ice, the molecules are very, very close together, right? That's the closest they can be. Well, actually, in ice, there's space. It's actually less dense, but they're interacting very, very strongly. And you have to put in energy to break apart that interaction and turn it into a liquid. And that energy is different from just warming it up. You have to put extra energy to break that. So then you've got water at 0 degrees C. You heat it up. It warms and warms and warms and warms and warms. And then when you get to 100, what happens, you put a whole lot more heat, and then it gas. So you break apart those interactions completely, and you have a gas. We talked about the difference in those states. So liquid, the particles are still closely associated with one another. In gas, they're totally separate. So you have to put in a bunch of energy to break those particles apart. Right? And this is this curve that shows that happening. One thing I want you to note here is the huge amount of energy that it requires to boil water. So at 100 degrees, to get 100-degree water to boil actually takes way more energy than to take 0-degree water and make it go to 100 degrees. Right? So that's only that much energy to take it from 0 to 100. Then you need this much energy to get it to boil. Way more. And if you've ever warmed a pot of water on a stove, Have you ever done that? Yeah. You probably noticed this, that the water gets hot really fast. You turn on that, the water hot pretty fast. But even after, it takes a while to actually, if you really want a strong boil, even once it's hot, you still haven't boiled it yet. It takes a lot longer. And this is kind of that it doesn't take nearly as much energy to warm the water as it does to actually boil it.
Is there, I mean, a good question, but I mean, if you get burned with water that's really hot but not yet boiling, is it that much difference? It looks like the temperature is staying the same now than
Right.
it was boiling.
Well, almost. So the better comparison is between steam and water, because water is still water. It's still in its liquid state, so that doesn't have all that extra energy. But if you get burned by steam, it is far, far, far worse. You're getting a lot more energy transferred to your skin being burned by steam than being burned by hot water. Yeah. And it's because you have to get all this energy down into your skin. And we're going to actually do some stuff that shows this and talks about this in lab next week on Tuesday. All right. Okay, so let's see what else we can figure out or what we can learn from something like this. There we go. So here's a question from your book. I'm going to stretch this out a little bit so it fits nicely, even though it's a little weird. Associate the contents of the beakers with segments on the following heating curve. I'm going to turn the lights off so you can see what these pictures are. So you've got, if you can see that, number 1 is boiling water. Number 2 is regular water, just water sitting there. Number 3 is ice cubes. Number 4 is a few cubes floating water. And number 5 is just water vapor. So let's start with number 1. Where does number 1 fall on this heating curve? Where do we see both steam and water at the same time? D, right? Yeah, good. So that's going to be number 1. What about 2? Where do we just see water? C, yeah. We just see water in C. What do we see in B? Which one do we see in B? 4. That's when we have ice and water as the ice is melting. So that just leaves A and E. Which one's which? Yeah. And E is 5. So first we just have ice, and then we have water. Did you know how that works? Now, one thing I want you to keep really clear here, it's a really common misconception that I hear all the time. What happens when water boils molecularly? What's happening to the molecules when you boil water and turn it into water vapor? It speeds up. They break apart, but what breaks apart? Yeah, let's look at this more carefully. So do you see these pictures? In these pictures, the red atom is oxygen and the white atoms are hydrogen. So you got little water molecules here. What do you have up here? Still water molecules, right? This is, a lot of people think that, or a lot of, it's a common belief that when water boils, water is breaking into hydrogen and oxygen. The bonds in that water are break apart, and you're forming hydrogen and oxygen atoms. That's not true. You still have water molecules when it boils. It's just that the molecules have separated from each other and you formed water vapor. So if this is a misconception that you had before right now, I'm sorry, it's going to stick with you. Even though I'm telling you that that's not true, and you, I'm sure, believe me, probably, maybe not, I don't know, but maybe you believe me that it's what I'm saying. Tomorrow, I might ask you the same thing. Well, I won't probably see you tomorrow unless you come see me, but another time I might ask you the same thing, and you'll go back to the hydrogen and oxygen thing. It's a weird thing that just is in our brain. So if you know that that's in your brain, make a note of it somewhere so when you come back and do your homework, you keep being reminded of that. And so when I ask about this on an exam in the future, I don't see that things that you're writing that hydrogen, or water boils and turns into hydrogen and oxygen. How persistent that misconception is. Like years and years of chemistry, and people will still say that, you know, like in college, and people will still say water boils and turns into hydrogen and oxygen. If that doesn't seem right, if that's like crazy to you, then good, you've already got it fixed, but I'm telling you, it's a common and persistent misconception. Yeah?
Like when the water freezes, the molecules getting back closer to each other, but when it freezes, like
Right. Yeah, exactly. And in fact, with water, we talk about this with density, the density of ice is less than the density of water. Ice takes up more space than water, which is why the thing pops open. So it's not exactly right that the molecules are packed in tight in water. They're not. They're packed in less tight. But individual molecules are closer to other individual molecules, and they make a cage-like structure with space inside of it. And that's the difference. So the molecules are more closely associated with one another, but rather than being packed in like little spheres, they're making these cages that allow for extra space. So that's probably a little confusing, and that's why it's not a great example. But pretty much every other substance, they do pack closer together. So if you take liquid, oh, I don't know, let's say some other element. Liquid hydrogen or liquid helium is absolutely more dense. The solid is more dense yet. So pretty much any other substance gets more dense as you change to the more solid phase. Water happens to be a weird exception there.
So what's happening to water when it continues to boil and boil? Like if you had leave it on the stove, it just disappears.
Right.
Is it destroyed?
No, the water itself is not destroyed. The water molecules are still intact. They've just dissipated into the atmosphere. So now you have more water molecules in your atmosphere. And that would be, you could see that by an increase in the humidity, what we call the humidity of the atmosphere. There'd be more water molecules in it. Another way you can see that, if you boil water and then have something really cold nearby, you'll see all the water molecules condensing in that cold thing as they boil out of the pot. Yeah. Good question. Any other questions about that? All right. Other ways that you can use heating curves is for substances that are completely unrelated to water. Any substance can have a heating curve, and they might be very different from water. Here's another question from the book. Whoops, that's not the one that I wanted to do. Okay, we'll find a different one. Sorry, thought I had this thing ready. Okay, this one here. I don't think we have time to work through this right now, but I want to show it to you, and we'll come back to it next week. The melting point for dibromomethane, some other compound, you don't have to know what that is. 53, and its boiling point is 97, so different from water. We can sketch a heating curve as this is heated from minus 100 C to 120 degrees C. So you should be able to draw these different states as it's heating, then as it's melting, heating again, boiling, and heating again, and show what state it is at any given temperature. Curve will help you determine what state it's in at different temperatures. So try this out. We'll come back and talk about this on Tuesday. Have a great weekend.